Okay, problem 2. There are 21 consonants, 4 prime digits, 5 symbols written on cards. We're going to choose 5 cards with no replacement. The question is how many choices that will have no letters. Okay? Now, a little simpler question that we can answer just to get ourselves warmed up when we encounter a problem like this is, well, if there's no excuse me, if there's no restriction, how many possible choices are there? Well, if there's no restriction, we've got what? 21 and 4 is 25 and 5 is 30. We've got 30 cards, and we're going to be choosing 5 of them. And the order in which they're chosen doesn't matter. We can rearrange them any way we want, and we still have the same cards. So there are 30C5 possible choices for the 5 cards. Now, most of those include some letters, and what we're after is the choices that have no letters. So this doesn't answer the problem. It's not even really technically helpful in answering the problem. It's not even necessarily relevant to solving the problem. But if we have this thought, it's going to be a little easier than to have the thought that we need in order to write down our solution, in order to figure out our solution. So, okay, now the question is, how many choices have no letters? Well, we're going to have to choose 5 cards, and they won't contain any of these 21 consonants. That means we're going to have to choose 5 of the cards which are either prime digits or symbols. Well, that's 9 cards. So we're going to have to choose 5 cards out of these 9 so that we can say there are 9C5 possible choices that have no letters. We're choosing 5 out of 9. So that's the answer. Of course, we can write that in factorial notation, or we can write it as 9 times 8 times 7 times 6 times 5 divided by 5 factorial. Whatever way you want to write it, that's the result. Okay? Now, we extend this just a little bit so you can see where this is going. Since this was mentioned, and I wrote this down mostly because somebody mentioned this very early, and I realized it was a good idea to have that thought. I also realized immediately that it was going to be possible then to extend this to the upcoming chapter. The extension is the question of what's the probability of getting 5 cards with no letters. Okay? Well, there are this many ways to get a card with no letters, and there are this many possible 5-card hands, so that the number of ways, or the probability, is going to be the number of choices that have no letters, the 9C5, divided by the total number of possible 5-card selections, which is 30C5. So we just divide this by this, and we get that probability. And just as a little more extension, this video isn't running too long. You don't have to watch the rest if you don't want to, but I'm just going to write down how those numbers work out. I'm going to do that off camera, then we'll talk about that. Okay, our probability is 9C5 over 30C5. 9C5 is 9 factorial over 5 factorial times 9 minus 5 factorial. And 30C5, I'm not going to read it to you, right there it is. When we divide 9 factorial by 9 minus 5 factorial, that's going to be 4 factorial. Everything from 4 down through 1 of the 9 factorial is divided out, and we're left with these numbers divided by the 5 factorial, which I've written here. And a similar thing happens with the 30 factorial. The 30 minus 5 is 25. 25 factorial is going to take care of everything in the 30 factorial from 25 down to 1, and we're going to be left with these expressions. Okay, now we're dividing a fraction by a fraction, which means that we multiply this fraction by the reciprocal of this fraction. So we turn this bottom fraction around, and we have this expression multiplied by this one. The 5 times 4 times 3 times 2 times 1 here divides the 5 times 4 times 3 times 2 times 1 up here. So that goes away, and we're left with 98765 divided by 30, 29, 28, 27, 26. Now, everything here is going to divide out. For example, 6 times 5 is 30. So the 6 times 5 is divided by the 30, gives us 1, so we don't have that anymore. The 9 goes into the 27 3 times, leaving us 3 down here. The 7 will go into the 28 4 times. Then the 4 can go into 8, leaving 2. And the 2 can divide the 26, leaving us 13. So we see that the numerator, let's see, I should have crossed the 7 out when I divided it into the 28. The numerator turns out to be just 1, and the denominator 29 times 4 times 3 times 13. So I barely have room to write that, but let's try 1 over 29 times 4 times 3 times 13. Now, 4 times 3 is 12. 4 times 30 would be 360. You subtract 12, that's 348. 348 times 13. 348 times 10 is 3,480. And 348 times 13 is over 1,000. So you're going to be up in the 4,000s, one chance in about 4,000, which means that this particular occurrence, no letters, when you have this many consonants, this many digits, and this many symbols, is pretty improbable.